recording. Oop. And there goes my Firefox chat. There goes. All right, now I can see things. Where's my right stick? All right. Oh, this exam is going to be hard to study for. I can see that already. Let's see here. No, don't do that. I would like you to not do that. I would like you to overlap it. Really? I like to select that. And let me guess. That goes all the way through. That punched a hole in my layer, didn't it? Yep, it did. Okay. Alright, we won't do that then. Okay. We will go ahead and turn that white with the fill. Fill. Where did my fill go? There it is. Oh, really? Really? Let's see here. Where'd it go? There it is. Fill the whole selection. There we go. Okay, now we can get started. Alright, so looking through the syllabus about this particular class, I noticed that Exam 3 is supposed to cover content from normal Exam 3 and normal Exam 4. So that means that there's a lot to go through. So I was expecting this to take 2 hours. It might be more. So whoever is in chat and or on my Zoom call can tell me not to do things because it hasn't been covered. And that should probably expedite our path through this material. Alright, so let's see here. I believe I have my right stick in working order. Nope, gotta change color to white. There we go. Now I can write. Okay, so as I like to start out, I like to start out by talking about the equations at hand in the exam at hand. All right, so we have the first, let's see here, these 4 equations here. These are the kinematic equations. Kinematic equations of motion. That's a lovely F there. Try that again. Of motion. They work just like the ones that we saw before from linear motion. So instead of x minus x naught equal v naught t plus 1/2 a t squared, we have theta minus theta naught equals omega naught t plus 1/2 alpha t squared. So all these letters, they're doing exactly the same thing as the linear letters we're doing that we saw in exam 1. So for every x, there's a theta. For every not omega, v, there's an omega. For a, there's an alpha. Let's see here. What else is there? So there's a force, becomes a torque. Mass becomes moment of inertia. What else do we have in here? I think that's the big important ones. Oops, sorry. Wrong torque. Tau torque, not gamma torque. Oh, and then and then P becomes L. And I think that's about it looking through here. So there's an exact correlation between all of these here. There's also an equivalence where we have that for a certain amount of theta that rotates, we end up with, let's see here, that's been x over r, the same as this equation over here. So r here being the radius of our circle, and then s is the distance traveled instead of x. And then so that means that there's a v on R, and this is an A on R. And similar story goes on through here. So this is, our force is equal to mass acceleration, therefore torque is equal to moment of inertia times angular acceleration. I believe there's an equation for that around here somewhere. There it is. But also, I believe, let's see here, there's another torque, where it's actually find the force in question. So it's force cross length vector, which is that's the vector form of our torques. But we don't bother with the vector form of that torque in this class. That's a little bit too much thought there. So we actually end up more often with, where is it? I think we end up with FR sine theta. And usually theta is equal to 90 degrees, and so sine of 90 is 1, and so we end up with FR, which I believe right here. This is FR that I was talking about. So sometimes it's R, sometimes it's L. The question is how far from it's a question of how far from the pivot you are. And if you're pivoting around a thing, that's a circular motion, so that's an R, which is why I've is R. But it could also be the length L of the lever arm and stuff like that. Here's our kinetic energy. It looks very familiar. It's very similar to this is our rotational kinetic energy, which is it's very similar to the translational kinetic energy, 1/2 mv squared. There's these i's here. The I is the moment of inertia. Usually it's given as mr squared for something that's going around a thing. But there's also tabulated versions for if you had something like, say, a disk that was going around in a circle, or a ring, or spheres, hollow, or shells, and what else is there? Rods going around the centers and around their endpoints and stuff like that. Oh, here's our, this would be a potential of, this would be gravitational potential energy here, which might be useful to us at some point. This is our radial acceleration, which I think we've seen part of before. This is the centripetal acceleration that we had in a previous chapter, and then when we had this v on r, we also were able to substitute this. We were able to rearrange this and turn and get this as an equivalent answer. Total kinetic energy, torques, work, power. This is angular momentum. Yep, I omega. That's angular momentum there. So this is angular momentum for an object with a finite where it's rotating around its some point that's approximate to itself. Like disks and spheres and such. Whereas this moment of inertia, this angular momentum here, this is for like a particle going around a thing, like say the moon going around the Earth, or the Earth around the sun, or yeah. So let's try to put these together, put them in a better frame. This moment of inertia is for a thing that's spinning, and this moment of inertia is for a thing that's going around another thing. So this is like moons, or let's say it was lab 3 where we had a ball going around on a string, and that'd be this particular case here. I think that's most of this stuff here. I think, yeah. Most of it's basically rehash of linear stuff in rotational frames. Scrolling up. As memory serves, elastic materials here usually gets the short end of the stick, so I'm going to ignore those for now unless it turns out I actually do need to do something about them. They usually don't get talked about very often in class, but Dr. Ford does make a point to talk about. He usually gets the problems where he has this young modulus where you take basically taking a rod and making you're compressing a rod like a pencil here. Oh, in with them. This is basically another version of the R. So if you got a going around a circle around a central point, this is L here, which is also the R. So quite often the L's and the R's will are interchangeable. They're both lengths. The question is, which one do you want, and how consistent do you want to be about it? So back to the Young's modulus here. Basically, if you're taking a rod and you're compressing it, or if you take a spring and you pull on it, you end up with this Young's modulus here. B is the bulk modulus for if you took a submarine and you put it down the bottom of the ocean, or mostly trying to crush things with at bottom of oceans or stuff like that. This is a shear modulus where you're basically trying to do this here, where you're trying to take a rectangular object or some other kind of object like this here, and you have offset forces, and you're trying to compress it this way. So you have a force going this way here and a force going that way there at the bottom, and the thing really wants to rotate, but for some reason is being held stationary, and so you're trying to shear it into pieces. But more often than not, like I said, these elastic moduli, they get ignored quite often, and so I suspect that given our compressed time, these concepts have been ignored once again. Then we have going to springs. This is our force of the spring again. It's back, and we're going to actually use it properly this time. This is acceleration, which basically comes from MA. And oops, try that A again. There we go. So you end up with this thing here, and we solve for A, and you get this over here. This is our angular frequency of a mass on a spring, right? Nope. This is angular frequency, period. For anything that has a periodic motion with some frequency, this is angular frequency here. If you have a frequency, this is how it relates to the period. Basically, the time it takes to repeat the motion. Here's our our potential energy for a spring, and this is our kinetic energy again. It's back, and then here we go. Here, this is the angular frequency for a mass on a spring, and then of course you punch this into here, and then you solve for F, and you go, oh look, here it is. So the frequency for mass on a spring, and the period for mass on a spring, and then these here are for a mass on the end of a string for a pendulum. These are pendulums here. Pendulum. For the period of a pendulum and the frequency of a pendulum. And this is mass on spring. Mass on spring. This is somebody has gone and done the differential equations and solved for these here. That's one way to do it. Or you could use energy conservation and solve that way. Get an ellipse and then solve it with that. And then once you have the position, then you can take the derivative, and this is the derivative of our position here. And I think that's about it for all of these equations here. Questions about the equations? Hearing none and seeing none in chats. Nobody's joined my Zoom. What's up with that? Oh well. Alright. So, nope, we don't want to move that. Come on. Can I? Nope. Oh. That's not exactly what I had in mind. Let's get back to the side here. Oh, for a Pete. If you want something done right, use mouse, right? No, I don't think I got anywhere on that, did I? Nope. Oh well. Can I make sure? Nope, it just wants to rearrange itself. Alright, fine, whatever. There we go. That's what I'm looking for. Okay. Back to the top of the exam. And we'll see how long far we can get. Alright. So. Okay, so let's see here. A uniform disc mounted on a frictionless axle, and that is perpendicular to the disc at its center. The radius of the disc is this much. At time t equals 0, the disc is at rest, but has constant torque applied to it, given constant angular acceleration. For the first 4 seconds, torque is applied to the disc until it is doing 8 revolutions. Oh, it turns through 8 revolutions. Okay. At t equals 4 seconds, what is the magnitude of the tangential velocity at point on the rim? Okay. So, let's see. It would like to know v on a point on the rim. So the point on the rim is r from the center, and it's going with an angular velocity of omega. We have r. We need the omega, y'all. Let's see here. Torque. In the first 4 seconds, torque is applied. We go through 8 revolutions. We know that theta is equal to 8 revs. And t is equal to 4 seconds. Theta naught equals 0. V naught equals 0. So that means we can find an angular acceleration. Theta is equal to, theta naught is 0, plus V naught, not V naught, omega naught. There we go. Omega naught is equal to 0. Omega naught t, omega naught is 0. We can drop that. So 1/2 alpha t squared. Solve for alpha. Alpha is equal to 2 times theta square root. All right. Did I get that right? Nope, that is not right. We have the t. Alpha is equal to 2 thetas divided by, there we are, 2 theta divided by t squared. There we go. All right, so we end up with 16 revs. I got a feeling I'm going out this long way, whatever. Per t for 4 seconds squared. So alpha is equal to 1 revolution per second squared. Okay. Now we have alpha. I need omega. All right. Omega is equal to alpha t. So that is 1 rev per second squared. T 4 seconds, and that is equal to 4 revs per second. Alright, now we get down to what we're looking for. V is equal to r omega. Well, got a problem here. That's in revolutions. So r is 0.2 meters. Omega is 4 revolutions per second. We need this to be in radians. There are 2 pi radians per revolution. Revolutions cancel. Radians is unitless, which leaves us with, let's see here, 0.2 times 4, no, 4 times 2 is 8, times 0.2 is 1.6 times pi, somewhere between 3 and 4. I should probably get a calculator to do that trick. 0.2 times 4 times 2 times pi. 5.03. 5.03 meters per second. Questions about that? Seeing none, which is possibly too fast for, oh, lovely. Possibly too fast for Twitch. Come on, scroll up. Alright. A uniform disk with a radius of this much rotates about an axis at its center. It has constant angular acceleration of this much and starts from rest. What is the radial acceleration of a point on the rim of the disk at an instant when the disk has rotated through this many revolutions? Well, okay. Alright, well, I'm going to keep going through this stuff because I'm recording it for everyone else who is not here. Alright, so we want A is equal to alpha r, right? What is the radial acceleration of a point? Radial acceleration. Oh, careful. A tangent. I'll go ahead and answer what this question is, but that is not the question it's actually asking for. A little more complicated than this one. It's like, what is all this information here? If you want A tan, no. It doesn't want A tan. It wants A rad. Oh, all right. Okay, fine. We'll get to that, but not right now. Soon. A tangential, which is not the question it's asking for, is alpha 0.8 rad per second squared times the radius of 0.15 meters. Radius again is unitless, which leaves us with 0.15 times 0.8, 0.12. 0.12 meters per second squared. That's not what the question's asking for. And it really should have that as one of the answers. Oh well. A rad. This is r omega squared. Okay. Oh, fine. Okay. We need omega square is equal to omega naught square plus 2 theta alpha. Alright? Yeah, that was about right. Cool. That's a 0. And this is actually exactly what we need. So I'm going to go ahead and write that in. So let's put in my 2. 2r omega squared being theta alpha. Okay, so then that is 2r 0.15 meters theta 6 revolutions, 6 revs, but that's 2 pi radians per rev. Those cancel out. And then, let's see here, alpha 0.8 rad per second squared. That's a rad, don't care about those. Meter per second squared, those are the correct units. What is the question? What is the answer? 2 times 0.15 times 2 times 6 times pi times 0.8. 9.05. 9.05 meters per second squared. Look at that. There it is. In principle, it could have asked what the A magnitude of A was. And then you have to have both of these here, and then you can do the Pythagorean theorem on that and find the answer to be squared plus 0.12 squared is that square rooted 9.04. Right? That doesn't sound right. That sounds really dumb. Oh, no. Oh well. It's more or less the same number. It should be just a touch bigger. 9.05 meters per second squared. Because this is a lot bigger than that number there, and so it all boils down to this 9.05. Let's see, we have another uniform disk on frictionless axle and rotating clockwise with angular speed of 12 revolutions per second. Starting at t equals 0, constant torque is applied that gives this constant counterclockwise angular acceleration. Wheel comes to a rest after 8 seconds after the torque is applied. How many revolutions does it turn through until it stops? All right. Let's see here. Let's see if this gives us the answer we're looking for. Omega squared is equal to omega naught squared plus 2 alpha theta. I can answer that with this. No. Not with that question. Not with this equation. Let's see here. I have a time. I need to know a distance. I don't have an acceleration. Okay. Let's try theta equal omega plus omega naught over 2t. I have omega is 12 revolutions per second. Omega naught is 0. T is 8 seconds, and we want to know how far it travels? Yes, good. One stop, very good. Answers in revolutions, velocities in revolutions. I will leave that as is. 12 revs per second plus 0 revs per second divided by 2 times 8 seconds. Seconds cancels all of these here. 12 plus 0 is 12, divided by 2 is 6. 6 revs per second. 8 seconds is 24 revs, I believe. Yeah, look at that. That number's over there. Let me check my math. I bet it is. Nope. It is not. I can't. I can math yet. Nope, don't move that. I would like you to select that so I can get rid of it. Nope, not with the delete. Z, 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 Z. There we go. Switch back to the 6 times 8 is not 24, it is 48 revs per not per second. There we go. All right. Thereabouts. Okay. Oh, and I need to. There we are. Two small spheres, each with a mass of this much, are connected by a light 1.6 meter long rod. Doink to doink. The sphere is rotated about an axis that is perpendicular to the rod at its center. Okay. Let's see here. The sphere is rotated about an axis that is perpendicular to the rod at its center. Okay. What is the angular speed of the spheres? The total kinetic energy is 1.28 joules. Okay. Oh, very well. All right, so we have kinetic energy equals equals 1/2 I omega squared. We want the omega, yeah? Angular speed, yeah, we want the omega. We have the kinetic energy. We need the I. All right. So here we have two objects going around in a circle, and so this is equal to mr squared plus the other mr squared, because that's on the other side, right? Two masses, 1 and 2, omega squared. One's here, mr squared, which means that this works out to these m1 and m2 are the same. Therefore, just make that m2 times 1/2 is 1. So we end up with mr squared omega squared. Kinetic energy. Solve for the omega. So omega is equal to the square root of kinetic energy divided by mr squared. We have all that, yeah? Yes. I'm going to plug in numbers. Square root of 1.28 divided by begin 0.02 times 1.6 squared. End, execute. 5. This is exactly 5 rads per second. We are not told the mass of the rod. Let's see here. The spheres rotate about, let's see here, 2 small spheres, each with a mass of this much, are connected by light. So the key word here is light rod. So we're basically told that the rod has no mass. But yes, if we were given a mass, then we'd have to go look that up. So if we were given a mass for that rod, then it would be 1/2 m1r squared plus m2r squared plus 1/12 ml squared omega squared, and L would be 2 r's. Try that. Let's be consistent about our r's. So then that would make this an r here, and you end up with a 4 here, so you end up with 1/3 r squared here, and this would be for the rod itself. But we were told that it was light, so therefore this mass is 0, and therefore we're going to ignore it. Otherwise, yes, we would have to take care of that. If the rod was to be considered, then its moment of inertia would have to be provided, because it would be an equation in a table somewhere, not providing the equation sheet, and so either they would tell you the I, or they would tell you the equation for I, given some information. But they said light, therefore it has no mass, therefore it has no I, and so we ignore it. A uniform disk with a radius of 0.2 is mounted on a frictionless axle at its center. The moment of inertia of the disk. So for objects that aren't points, the I will be given. The I will be given, or a formula for the I will be given. One or the other. Yes. I think we might just get to that. Or at least the I should be given. The moment of inertia for the disk, yep, like this one right here. So the moment of inertia for this disk here is given here. So here's the I for an object which is not a point. Light rope is wrapped around the disk, and a block with a mass of 10 kilos is suspended from the free end of the rope. The system is released from rest. What is the speed of the block when it has ascended a certain distance? Alright, going here. I should probably not overwrite important information. Alright, we have an H here. We are told an I for this. We want to know speed. Alright, so that sounds like that's an energy conservation question to me. So we have energy that we started with is equal to the energy that we ended with. The energy that we started with is our potential energy in the block. Was for 4 was B. Unless I manage to mess something up this here. I have ways to find out. This was this year exam. I should be able to find that this year. Exam 4 F19, 18, 19. No answers. Answers F. That's F4. We don't want that one. Exam 3. 19 answers here are. Interesting. What did I do? That gave me, I see, yes. Interesting. Let me have a look see at what I told my calculator. 1.28. The square root, let's see here. Kinetic energy, 1/2. This here. Yes. Indeed, Dr. Ford did say that the answer was B. Let's see here. Let's see if we can figure out if I screwed something up or if Dr. Ford screwed up. Let's see here. So our kinetic energy is 1/2 is equal to 1/2 I omega squared. We have some points going around in circles. That's an mr square. 1/2 goes there. Mr squared goes there. Mr squared goes there. We have 2 of them going around. Yeah. Oh. I better know what I did. Yeah. I know exactly what I did. I put the wrong R in. Oops. Congratulations, Dr. Ford. You got me. Good job. Yes. This is L, which is 2R. Which means that the R I put in here is not 5. Yes. So from here to here is 1.6, and that's not the value I need. I need the value from here to here, which is 0.8. And that was here. So it's here. So I have this, all right? Yep, and it's on the bottom. So when it gets out, let's see here. It have the R, square it, move to the outside, becomes 1 over 1/2. So then we end up with times 2. And this answer is for people who forget about L being 2R. And indeed it is 10 radians per second. Better? Yes, much better. Now back to this question here. So we start out with potential energy, and then we end up with a kinetic energy. Oops. We have kinetic energy translational plus a kinetic energy rotational. So we start with mgh, and that is 1/2 mv squared plus 1/2 I omega squared. It wants to know the speed of the block. All right, so then we will we'll turn omega equals v over r to v is equal to, nope, that's exactly what I need. And we're given an I. Yep, yes we are. So we end up with 1/2 mv squared plus 1/2. When we put this in here, we get the r squared. We get an r, 1 over r. We square it, put it underneath the I over r squared, v squared. If there's more simplifying we could do, doing it this way makes it easier to do those simplifications. I'm not seeing those simplifications pop up, so I'm not going to really do that. So let's see here. All right, where was I? Let's see here. M, you're told mass, right? Where'd you go? Yes, 10 kilos. I'll move it over here. Nope, I'm just going to punch numbers in. So we have 10 kilos. Clear that. 10 kilos times 9.8 for gravity times the height we fell of 4 meters. 392 joules for initial potential energy. We have 1/2 mass, v squared, which is 10, right? You have 10 kilos there, so 10 divided by 2 is 5. Plus I is 1/2 times this 1/2 is 1/2 is a quarter, and then the radius is 1/5 squared. So we end up with, oh boy, a quarter and 5 squared kilos v squared. So that works out to 5 plus 5 squared over 4 is 11.25 kilos of velocity squared. Therefore, V is equal to the square root of 392 joules divided by 11.25 kilograms. Or 392 divided by 11.25 and execute 5.9 and change. I'm going to need a beverage. Be right back in about a minute. And we have added hazard to and a green object to a green screen to this whole situation. Yep, and make a mess. Make a mess all over everything. Let's not make too big a mess. All right. Hopefully, my voice will not be the limiting factor of this review. That would be most unfortunate. All right. That'd be very unfortunate indeed. All right, uniform cylinder. So here we are. Yep. So here's the other case where instead of telling us what I is, they give us an equation for I. Uniform cylinder of the mass of this much and radius of this rolls without slipping on an incline. At the bottom of the incline, the translational speed of the center mass of the cylinder is this much. The maximum vertical height. What maximum vertical height above the bottom of the incline does the cylinder reach? All right. Oh, it goes up. Okay, yeah, I see that. Okay, all right. Well, v being squared, it doesn't matter if it's going up or down. It could be going. It could have started here at 0 and then it reached bottom going 8 meters per second. Goes. What is the original height of the object? Either way, same thing. So, energy initial is equal to energy final. Energy initial, we start with 1/2 mv squared plus 1/2 I omega squared is equal to mgh. Rolling through again, we end up with 1/2 mv squared plus 1/2 I, we are told is 1/2 mr r squared. And then omega, using the same omega up here, becomes v squared on r squared. Those cancel out. Is equal to mgh. mgh, like that. And then the m's cancel out from both left and right. That is not a thing we can do with this one up here. So you can't just go through and scratch out all the m's just because. You have to actually know that all the m's are indeed equal to each other, and because we're talking about the same object, that's the thing we can do. So we're left with 1/2 plus 1/4 v squared. So 1/2 plus 1/4 is 3/4. 3/4 v squared is equal to gh, and we're looking for h, yeah? Yeah. All right. H is equal to 3/4 v squared on g, punching in our given numbers. 0.75 times our velocity 8 squared divided by g, 9.8, is 4.9. 4.90, yep. 4.90 meters. A 5-meter long bar is horizontal and is pivoting about an axis on one end. Okay. Now with a pivot, and is pivoted about an axis at this end here. What is the magnitude of torque produced by a horizontal force F that is applied to the other end of the bar? Oh, okay. Alrighty. So, this F here. Control Z. Control Z, Z. Torque is equal to torque vector is equal to F cross L. Also known as, we're looking for just the magnitude of this thing, F L sine theta. What the book will do, they'll say this is F perpendicular to L. Well, mathematical statement for saying that, that's F L sine theta. Alright, well, this angle here, that's our theta there. So we end up with F L sine of 180 degrees. Oh, well, that's 0 Newton meters. Another way to look at that is like, oh, this F is parallel to my L, therefore there is no perpendicular component of my F, and so 0. Moving right along, yeah? Boink, boink. Top page. A uniform bar with length of 0.8 meters and mass of 1 kilo is attached to a vertical wall by a frictionless hinge. The bar is held in a horizontal position by a light rope and makes an angle of 36.9 degrees with the bar. Okay. The rope is attached at the wall at the other end of the bar. Yep. What is the vertical component of the force that the hinge exerts on the bar? Okay. Oh, that's really handy. Right, vertical component of the force. Oh, that the hinge exerts. Interesting. Let's see here. Alright. Okay. Okay, that's going to take a little bit of thought there. That's not very handy at all. It wants the hinge's force. Oh boy. Okay. Oh boy. Okay, let's see here. We have we got tension going this way. We got gravity going this way. Try that gravity again. And we got force going that way. Okay. All right. I'm gonna start with my torque. So we have three equations. Let me see here. I'm gonna pop these off. One, doink, 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 doink. So we're looking at these here. The first and second conditions for equilibrium. Basically, all the forces in the x direction equal to 0, all the forces in the y direction equal to 0, and all the torques are equal to 0. And that is the question we are trying to answer: is what forces do we need to make all these work out to 0, or at least enough information to find the vertical component of this force? And that could be a fair number of steps. I'm going to start with torque. Torque is equal to 0. Is equal to mg half, mg L half, mg L half. This is my torque from gravity pulling down in the middle of the rod, minus tension L, and then we need this here, the sine of this angle here. Yep. Sine of 36.9 degrees. All right, divide the L to the other side. That makes life a lot easier. Make this equal, and then we forget about that. And we want the tension. Yeah. Oh, actually, let's see here. This number here is exactly what we need, right? I think this number is exactly what we need, right? Yep. mg, yeah. Okay. So this value here, this is my torque in the vertical direction. That is exactly what I need for this next step. So I'm just going to go ahead and immediately say that this is mg half. So now I'm going to sum my forces in the y direction. And so we have the force of the hinge going up, the force of the, let's see here, oops, let me back that up just a touch there. Oh yeah, that's right. Force of the hinge in the y direction plus the tension in the y direction minus my force of gravity. And this is all equal to 0. So now I need the force H in the y direction, and that is equal to force of gravity, mg, going up, minus mg half going down, right? Nope. Mg going down, mg half going up, which means that my force of the hinge in the y direction is just mg half. So it's basically carrying the other half of this rod here that the tension isn't also producing. Let's see here. We're told the mass. There's our mass, and we already have gravity, so it's 1 kilo. Gravity is 9.8, so that works out to 4.9. Up. Let's see here. Oops, come on. Nope. There we go. And all right, more water. Oh, careful, I might need some tea here. I might need tea intermission. All right, a 5 meter long bar is pivoted about an axis at its lower end. If the bar is at this angle here, above the horizontal, what is the torque above the axis produced by a horizontal force 4 newtons applied to the upper end of the bar as shown in the sketch? Okay. All right, so in this particular case, let's see here. So we got 36.9 degrees here. Goes that way, horizontal. We need this angle. We need this component here, and this here. We end up with this angle here being this theta here. I think that's what we're looking for. There. Yeah. Okay. All right. There should be. There's probably some parallel line theorems out there that we can actually prove that with. Oh, nope. I'll be very careful. Like I said, gotta use the parallel line theorems. All right. So this is theta here, and this is phi minus theta. Right? Nope. You gotta be careful. 90 degrees minus theta. You gotta be careful there. Wow. I about ready to screw that up most royally, wasn't I? So we need a torque equal to FL sine of some angle. Oh, bugger. I need the angle between, so let's see here. If this was going up this way, then this angle would be 0, right? Yeah, and this one would be 90. Yeah, 90 there, 0 there. And so then I would want sine of theta or FL cosine of phi. All right, well, I want to stick with that theta there. So F is 4 newtons, 5 meters out, sine of an angle, 36.9 degrees, 0.9 degrees. So that's 20, figure that, 20 sine of 36.9, 12 Newton meters. So scratch those there, doink, doink, doink. And then, right, we know it's the smaller one because this is the smaller angle here. If this was 0, then there'd be no torque. So we should be closer to the smaller value, which is 12 values, good. We're going in this direction, which is clockwise. Oh, let's not go too far out of bounds. There we go. A uniform disc with a radius of this much is mounted on a frictionless axle, and the moment of inertia is provided, be 1/2 kilogram meter squared. Light rope is wrapped around the disc and block is suspended from the frame of the rope. System is released from rest and the block descends as the disc rotates. While the block is descending, the tension of the rope is 40 newtons. What is the acceleration of the block? Oh boy. Okay. Okay, let's see here. Okay, all right. We are told, all right. I believe that this is going to turn out to be a force question. So we have mg down, tension up, which means we end up with a tension going this way. We're told that this is 40. Uniform disk. So much we got an I for that. So then this turns into a torque situation where we have I alpha is equal to TR. Oh. All right. Okay. Well, that's rather quite handy. I don't care about this. That is irrelevant. What I care about is this one right here. I mean, I could go about all this information here and do my algebra and whatnot, but I can find that alpha is equal to TR over I. We are told T is 40 newtons. We are told that the R is, let's see, where to go, 0.2 meters. And the I is 0.5 kilograms meters squared. All right. So that works out to 40 times 0.2 divided by half is 16. All right. The kilograms comes out of the newtons, so that becomes a meters squared per second squared. That meters squared, let's see, it goes out. Those units don't look so. Yeah, nope. Yeah, we're good. So we end up with a meter times a meter is a meter squared divided by meters squared there. So that leaves us with a per second squared from the force, and so there's that. So it's 16 inverse seconds squared, which is the same as 16 rads per second squared. Alrighty. So now we have alpha. Now I need the A. Right? Can we do that? Uniform disk? Yep. We're still good. And that becomes alpha times R. 16 rad per second squared times the radius of 0.2 meters is 3.2 meters per second squared. Back to the top. Oh, for the beat. I usually bounce things around all over, whatever. A man holding a heavy mass in each hand is standing on a horizontal platform that rotates without friction. All right, so we got a guy sitting in a chair going around in circles. All right, with his arms outstretched, like so. The moment of inertia of the system, platform, man, and mass is 20 kilograms meters squared, and is rotating at 30 rads per second. The man then pulls the mass into his sides, and the moment of inertia of the system becomes 15 kilograms meters squared. What is the kinetic energy of the rotating system after the masses are pulled in? Alrighty. Alright, two-step problem here. So the first part is we need to do our conservation of angular momentum. Like so. We're told this number and that number and this number here, so we find that omega final is equal to I initial, omega initial, divided by I final. I initial is 20 over 15. Those units cancel each other. Omega initial is 3 rad per second. And so we find that, and that's here, but we can do better than that. 15, 3 over 15 is a fifth. 20 over 5 is 4. Now we need the kinetic energy. And so that'll be 1/2 I omega squared. 1/2 I is 15 times the omega of 4 squared. 15, and clear that. clear again. 4 squared over 2 times 15 is 120 joules. This is what is known as could be thought of as an inelastic collision, because I know that 1/2 I omega squared for first situation, 20 times the, let's see here, 3 rads squared is not 120 joules. It is in fact 9 squared over 2 times 20 is 810 joules. Yep. Okay. So some energy was lost for having brought the masses inwards, bringing his masses inwards, decreasing his moment of inertia. He went faster, but because his I decreased, he also lost some energy to that. All right, 15, 20, 30. Yep. There's some energy lost in there, which, depending on purposes, may or may not be a good thing. One end of a uniform bar that is 4 meters long, and has a mass of 5 kilos is attached to the floor by a frictionless hinge. Yup. A light horizontal rope attached to the upper end of the bar holds it at rest at an angle of 53 degrees because parallel lining theorems. What is the tension in the rope? Okay. So we have, going downwards, a mass of mg at half length. Oops. No, let's not put that there. Okay. So here we only need to deal with our torques. Only a torque problem. So we have tension at L at sine theta minus mass gravity at half L sine its theta sine phi, which is this angle here. So that means that phi is the complement of 5 at 53.1, which is 36.9. I think that works. Yep, that works. Or we can rewrite this so that we have cosine of theta. That'll make life easier if we just use cosine theta, so I shall. This is all equal to 0. So L cancels out. Divide to the other side. So we have that T sine theta is equal to mg half cosine theta. All right. T is therefore equal to mg cosine divided by sine is cotangent, or 1 over tangent, and I'm going to do that. 2 tangent theta. I'll go ahead and punch the numbers in. Mass is 5 kilos. Come here. 5 kilos times length of 4 meters divided by 2 times the tangent of 36.9 degrees. Nope, that's not right. Wrong angle. 53.1. There we go. That looks better. Nope. I do that right. I got a sneaky suspicion I did something funny here. Oh, I don't care about L. What am I putting 4 in there for? It's gravity, 9.8. We'll wake up yet. And then double check, make sure we got the 2 tangent 53.1. Yeah? 18.4 newtons. Hot dog, look at that. Still no one in my Zoom. Interesting. Whatever. Let's see here. 8-meter long uniform bar with mass of 10 kilos has one end attached to the floor by a frictionless hinge. 8 meters long, 10 kilos of mass. Okay. Bar is released from rest at an angle of 53.1 degrees above the horizontal. What is the angular acceleration of the bar just before it is released? Moment of inertia for uniform bar of length m and l is given as 1/3 ml squared. Very good. All right. So force is equal to, nope, not force, torque is equal to I alpha is equal to F L sine theta. Let's see here. I'm gonna make sure that I got this number right this time. All right. 90 minus 53.1, 36.9, right? Yes, good. We need, what is it for? Angular acceleration, this one right here. All right. Okay, F, so I is, where'd it go? 1/3 ml squared is equal to force of gravity, mg, L, sine theta. And we need the alpha over here. There we go. M's cancel each other. We don't care what the m is. Move the L to L squared to the other side, so this becomes 1/L. And then multiply that 3 to the other side. So alpha, try again. Alpha is 3 G on L sine theta. So punching our numbers in. 3 times 9.8 divided by the length of this rod. Oop, hold on a moment. Nope. Getting ahead of ourselves. Where's the force of this thing? It's in the middle. Torque is applied at half the length. Put 2 over here. There we go. 2 times the length of this thing, where'd it go? 8 meters. Times sine of 36.9 degrees. Because we want this angle here again. And so that is 1.10 rads per second squared. There we have it. Any questions yet? Hearing none and seeing none. Oy, so much circular motion. I mean, I love circular motion and all, but I also like the oscillating masses too. Hopefully get to that soon. A star has a mass m of this much and a radius of that much, and is rotating about a diameter with an angular speed of this much, about a diameter, okay? The star then collapses to a radius of this much without losing any mass, which is not likely at all. A star can be treated as a uniform sphere, which is probably not true, but we will today, with a moment of inertia of 2/5 mr squared. What is the angular speed of the star after it has collapsed to its new radius? Alrighty. So, I omega initial is equal to I final omega final. We need the omega final. What is the angular speed? Yes. Omega final is equal to I initial omega initial over I final. All right, well, I got 2/5 in top and bottom, don't care about those. You got M on top and bottom, don't care about those. It's the R. R is what I'm going to care about today. R squared, actually. So it becomes R initial squared omega initial divided by R final squared. Our initial is here. We have 8, oh boy, times 10 to the 8 squared. Kilograms is, no, omega. 3 times 10 to the minus 6 rad per second divided by 4 times 10 to the 5 squared. At least I'm talking about this out loud because that is terrible handwriting. Clear all that. 8. 8 squared times 3e minus 6 divided by begin 4e5 end squared. Execute. 12. Rads per second. Which for a star is moving quite quickly. Yeah, that would be 12 divided by 6 is about 2 revolutions per second. So 120 revolutions per minute. Yeah, it's moving. It's moving at a pretty good clip there. Just out of curiosity, let's see here. So 12 rads, clear 12 rads per second times 4e5. Oh, let's see here. So that's 4.8 million meters per second at the equator. Not quite. 300 and then another 1, 2, 3, 1, 2, 3. Multiply that by 100. So 1.6% the speed of light. So it's moving at a pretty good clip there, but not quite fast enough to be of significant concern before special relativity starts doing weird things. All right, block with mass of 4 kilos is attached to a horizontal spring with a force constant of K. Block moves in slow harmonic motion in a horizontal frictionless surface, amplitude of half a meter. Maximum acceleration is 20 meters per second squared. What is the force constant of the spring? Alrighty, springs, woo, oscillating motion. All right, let's see here. We are provided an equation somewhere, right? We are told that from derivations, forces of the spring is kx, and that is equal to is equal to ma. Therefore, k is equal to ma over x. Yes. Our amplitude. These occur at the same time. So we get our mass of 4 kilos. Acceleration is 20 meters per second squared divided by a half meter. Meters cancel each other, and from the lab that we had way back when, that's a kilogram per second squared, which is correct units. That's good. So that's 40 times 4 is 160. Kilograms per second squared which is the same thing as 160 newtons per meter. Oh, good. There's 3 of you here. Pretty good. All right, let's see here. A block with mass of this much is attached to a horizontal spring. It has a force constant of this much. Block moves in horizontal friction on the surface, or motion amplitude this much, maximum speed. Alrighty. Okay. There's a few ways to go about this. So we have maximum displacement with our kinetic energy of maximum displacement with a potential energy 1/2 kx squared equal to our maximum velocity 1/2 mv squared. The halves cancel each other. We have the x, we have an x, we are looking for the v, yeah? Yes. Therefore, v is equal to x square root k divided by m. This would also be equal to x omega. Well, x being our maximum amplitude being a, so you probably more likely to see that as a omega. Alrighty. So I believe we have all that information. That's 0.4 meters. Square root k, where we go? 640. Yeah. Newtons per meter divided by our mass of 10 kilos. So 640 divided by 10 is 64. Square root of 64 is 8. So that becomes 8 times 0.4 meters per second, which is 8 times 0.4, 3.2. A block is attached to a horizontal spring and moves in simple harmonic motion on a horizontal frictionless surface. Okay. Amplitude of the motion is 0.32 meters. Frequency is 4 hertz. What is the frequency when the amplitude is changed to half that for the same block on spring? Well, let's see here. Frequency is equal to the square root is, let's try again. Frequency is proportional to the square root of k on m. I believe f is, that's a 2 pi. I believe, memory serves, k on m. There's a equation sheet for that. Notice that the amplitude does not play a part in the formula for frequency. So that means that the frequency is unaltered from 4 hertz. Any questions yet? Have I blown past some thought and you go, because Twitch can only go so fast? Because Twitch has latency. Oh, come on. Whatever. A small object of the mass of this much swings on a pendulum on the end of a long light rope. For a small amplitude of a swing, the period is 3 seconds. If the object is replaced by one with mass of this much, of twice as much, what's the period for the swing? Let me get the actual equation this time. 2 pi L on G. All right. Well, period is 2 pi L on G. Is the mass of the pendulum in there, of the bob in there anywhere? It is not. So the period is unaltered. A wire. Oh, look at that. Did you guys talk about Young's modulus? I don't think you did you? So this is one of Dr. Ford's exams, and he makes sure he is certain to talk about Young's modulus. But you guys have Wu and Vladimir, so you may not have talked about Young's modulus. And also, we lost a week, so I'll give you a few seconds. Did you guys talk about Young's modulus? I don't think you did. Alright, yep, I had a sneaky suspicion as much, so we will go ahead and leave Young's modulus spell alone. A block with, yeah, I'll go ahead and leave Young's modulus alone. We got places you could be and things to do here. It'll probably not be on the exam. Block with mass of 2 kilos attached to a horizontal spring with a force constant of 400 newtons per meter. Moves in motion on horizontal friction surface at one point in the motion. Block is 0.3 to the right of equilibrium position and is moving left with the speed of this much. What is the amplitude of motion? Alrighty. Kinetic energy. No, energy conservation. Energy initial is equal to energy final. Energy initial, we have the potential, 1/2 kx squared, plus the kinetic energy, 1/2 mv squared, is equal to our energy final, which is our amplitude, which is going to be our potential energy, 1/2 kx squared. Alrighty. So plugging all the information in, we have 1/2 k, where'd it go? 400 times our displacement of 0.3 meters squared plus 1/2 mass of 2 kilos times the velocity of 5 meters per second squared is equal to 200 newtons per meter k x squared. Alrighty, so we have 200 times 0.3 squared. 1/2 of 2 is 1 times 5 squared is right, 5 squared, yep, 25. So that's 43 joules is equal to 200. Let's try that 200 again. (200 newtons per meter x squared). Therefore, x is equal to the square root of 43 divided by 200, and that is 200. There we go. We'll get a number in there yet. 0.464. Alrighty. 464 is more than the 0.3 that we were spotted at. Yeah, very good. Because we have more energy than just our potential energy, we also have this kinetic energy. So we can go further than just the 0.3 meters. Alrighty. Questions about that? So I've gone through exam 3, but we have had a compression on this semester, and so there is an exam 4 material that also needs to be covered. Are there any questions about rotational, kinematics, about the rotational stuff, or the oscillating springs and pendulums, anything about that that I need to go back and do again? Not hearing any. All right, question 17. Okay, we can do that. Question 17, come here. Nope, that's not 17. 17, this one down here. All right, so if I get my R in here, I can turn that all. This one right here, I'll turn that all white. Come here, Phil, and that, and boink, here. Really? Come on. I would like to turn that. Why is this not turning white? That's rather quite unhandy. That's weird. Alright. Oh, I know what the problem is. Let's go ahead and write on the proper surface. Come here, Phil. There we are. That helps. That helps a lot. Alright. So, we are told we're told all this information here. We need to be writing with that. So, frequency. Let's see here. This one? Nope. This one. We are looking at frequency, motion, spring and let's see here. Mass and spring, right? So mass and spring, we are looking at frequency. Frequency for mass and spring. Oop, yep. I wrote that down wrong. Shame on me. Oh well. Turn that black. There we go. Frequency is 1 on 2 pi square root of k on m. K on m. When the amplitude of the motion is 3.320 meters, the frequency is 4 hertz. When the amplitude is changed to half that for the same block and spring. Oh, well, the spring is K is still whatever it is. Mass is still whatever it is, which means that K on M is whatever it was. We are told that this is equal to 4 hertz, and so this number is unaltered. These quantities are unaltered, so that means our frequency is unaltered. Make sense? Let's see here. Pull that up. Okay. So now, there's a bunch of thermodynamic problems, I believe, that are in order. Possibly some other thoughts here, yeah? Oh yeah, and the waves. Yes, that's right. That's right. Waves and thermodynamic and some thermal stuff. I don't know exactly what all he got covered through here. All I have is what the syllabus says. And what does the syllabus say? Document viewer. Syllabus says, okay. Waves, standing waves, interference, sound, expansion, heat transfer. That all sounds, that may or may not sound familiar to you all this year. So, all right. Let's talk about what all equations we have here in front of us. as is my habit when starting off a new exam. Okay, so let's go ahead and write on this surface. Alright, so we have velocity of any wave. Any wave for which we have an f and wavelength. So let's draw a wave here. If it is traveling, say it travels that way, we have a frequency, we have a wavelength here, lambda, and then a frequency for how quickly this thing will oscillate up and down. And then you can relate frequency and wavelength to this velocity for any wave. For a wave on a string, we have this case here where we have the square root of tension over its linear density. We went over that in lab 7? Yes, lab 7. This here is the equation for the string going from left to right for how it travels in time. So we have its frequency here, we have its velocity, and we have the amplitude, how far up or down it goes, amplitude there. This has been rewritten. So instead of in terms of frequency and velocity, we have it in terms of wavelength and period. The equations that we had in the previous case, let me pull those equations. Oop, no, don't do that. These equations here relating angular frequency to frequency and frequency to period continue to apply to these traveling waves up here. Let's see here. This is for, let's see here. What do these go for? These are for the frequency of standing waves. If we have a string the frequency of this the frequency of a standing wave on the string is related to its length, the velocity at which the waves will traverse it in, and a number n. It can be any integer above 1. If, on the other hand, let's see here, this one is for the particular case where you have, say, a standing wave in a pipe where one end is open and the other end is closed. This is the equation they'll apply for standing waves in a pipe. This will also apply for standing waves in a pipe with both ends closed, which is similar to the string, or with both ends open. Let's see here. I would like a little more space to be writing. Intensity is, oop, look at that, there's a bug on my screen. Nope, now it's on my finger. This equation here, this is intensity, which is the power delivered by a wave from a point source. So it's divided by the surface area of a sphere, given how far away you are from that point source. And then this is about the loudness measured in decibels, where I naught is a reference intensity, which is something like, I think it's 10 to the minus 12 watts per meter squared, something like that. F beat is equal to being F1 minus F2 is a case where you have two waves with a certain frequency pretty close to each other in order for you to hear it. If, let's like say, you had a reference of 440 hertz and you're trying to tune a string to that 440, but you're at, say, 441 hertz, you would hear a pulse where they would cancel and then reinforce each other and then cancel each other once every second. And that's that F beat there. This is Doppler shift here. I prefer to write it as plus or minus, and then you need to pick plus and minus to make sense. So if you had, if you're standing still, then your listening position would be 0, and something comes racing at you, you would expect the frequency to increase. So you would need to pick the sign to make this value here increase, which would be a minus sign, so that the frequency source would be higher to that frequency, would be higher for the listener. And so you end up with V over V minus Vs. Here we have some unit conversions here. So we can convert Celsius to Fahrenheit, Fahrenheit to Celsius, Celsius to Kelvin. This is basically this here. But basically it's trying to say that a change, this is basically saying a change in, a change per degree Celsius is equal to a change of 9/5 of a degree Fahrenheit. These three, right? Hold on a moment. Oh, no, we gotta be careful there. These two here, these are for thermal expansion of a linear object, like so, and the expansion of a volume object, like say a flask or a cube of metal. This is pressure, and this, I'm not sure what that is. I'm not completely sure what this one here is, so I probably won't see that. And if we do see it, and then I'll know exactly what it's all about. This here, these equations here, these are about heat transfers. So we have, let's see here, this would be Q, this would be for heating or cooling a material. And this one is for melting or freezing a material. This one here, this is for conduction here, conduction. And this is for radiation, where you radiate some heat away because of because it has temperature. And this is you're moving heat from a hot place to a cold place over a certain length L through a surface through a surface area with area A, and K is the property of the material. Radiation, it has a certain area. E is a property of the material in question, and sigma is a constant. Sigma is given here for us. This year, what else have we gotten to? Let me double check to see if I haven't gone past some. Let me check the syllabus one more time. So heat expansion, heat transfer, heat. I think that looks like about it. Yeah. That looks like about it for this exam here. So we'll see if we can't keep to that. According to the syllabus, this here. This is exam 3, and this exam is final. That's final. And we are skipping and the professors appear to be skipping all of this stuff here according to the syllabus. So any questions about these equations here, and have I gotten that right or wrong? Is there any topics which I have talked about which we are not actually in fact doing? seeing none. Go ahead and turn back on the higher layers, and we'll go through these problems until we find that the problems have we've gone through all the problems. Gone through all the problems that the syllabus says. Alright, scroll up to here. Alright. You are standing midway between two stereo speakers A and B, boink, boink, A and B. They are located at a distance of 20 meters from each other. Yep. Speakers are emitting waves in phase with the same wavelength of 3 meters. Okay. Initially, you are standing at point P, that is midway between the speakers, a distance of 10 meters from each speaker. You then walk a distance x towards speaker B to point Q. You observe that sound from the first speaker cancels you observe that the sound from the speakers first cancels when x is equal to what? Okay. Let's see here. Okay. I'm going to go ahead and bring this to the top because there might be an equation which might be helpful to us in here. And again, there may not be. Alright, no, we are going to have to reason through this ourselves. How fun. Okay, So, okay, 3 meters, right? So they're in phase. So, I should, make sure I need to draw on the right surface. There we are. Okay, so this goes up, and then 3 meters later, we're up again, and then so we start out up here, and then somewhere, and then another up there 3 meters later. Let's see here. We need to be at, we need a distance. Oh boy. My thinker is going to have a hard time thinking through this one. Alright, we need a distance. You need a... You gotta think through this. Okay. Alright. We get... Let's see here. 10 meters plus x needs to be equal to in lambda. 10 meters minus x needs to be equal to let's see here. M lambda? Gotta be careful here. Because we need to make sure that we don't cancel lambda, or we're gonna be in a world of hurt. This is rather quite unhelpful. Okay, I'm going to break this thing. I'm going to break this diagram into two shapes here. So we have A here, and we're going to have some distance out. and then we're going to have a B here. And then this needs to be, so then this, let's see here. This is 10 plus x, and this is 10 minus x. And this interval here needs to be in lambda. There we go. So then I can take the difference of these here, right? Yeah. So I take the difference of these, subtract that from that. So I find that this is equal to, take the difference there, this becomes 2x. There we go. Now we're getting somewhere intelligent. All right, very good. Okay. So now we end up with 2 lambda, in lambda on 2 is equal to our x in is some integer, so integer half, and this is 3 here, so we end up with 1 half, or 1 or 3 halves, or whatever, 2 times 3 meters. Okay, so the first one we have 1.5 meters. Look at that. There we have it. Ta-da! Oh, hey, that hurt. Let me make sure that my head that was worth it. Oh, come here. Come here, previous exams. Okay. Nope. Go forward. This was fall of 19. Where do you go? Fall of 19 answers. Here we are. Uh-oh. 3/4. Bugger. Where did I go wrong? Oh, dear. Why? Oh. Right. I know what happened. So this is actually a constructive point here. So in lambda means that I go through in cycles from here to here. But I don't want in cycles. I want half a cycle. So that when I get, so if I go in cycles like that, then they interfere constructively. I don't want that. I want them to interfere destructively, like so. Now that means I need to be half that, which means that this is not half, this is quarter. Which means that, and also we want the first one, which means we want just 1 here. So we end up with 1/4 lambda, which is 3 on 4, 1.75 meters. There we are. Did I screw that up badly enough that you guys don't understand, or so I need to do it again? Or are we fine? I feel I need to do it again. Okay. Alright. We'll see. A wire with a mass of 1/2 kilo is stretched so that its 2 ends are tied down 1.25 meters apart. The wire vibrates at the fundamental frequency of 40 hertz. What is the speed of the propagation of the... Yeah, it was painful. What is the speed of the propagation of the transverse wave on the wire? Alright. Okay. So we have a standing wave here, yeah? Let's see, standing search. Okay, yeah. I don't think we need to know what the mass of this thing is. But that's a fairly heavy wire. Alright, so we have that from here to here, fundamental mode. Okay, yep. So it looks something like this. This is 1.25 meters long. We're told that F is equal to 40 hertz. We need to know speed. Okay. Okay. So v is equal to f lambda. Oh well, if it looks like this, well then my other wave is over here, so this is actually lambda half. So that means that lambda, so I have my 40 hertz here. Lambda is 1.25, double that is 2.5 meters. So that turns out to be 2.5 times 40 is 100. 100 meters per second. There we go. 100 meters per second. Ta-da! Okay. A pipe has length of 1.2 meters, is open on one end and closed on the other. Oop. So it looks something like this. What is the wavelength of the fundamental standing wave for this column of air in the pipe? So we have a wave that looks something like this. Oh, that's terrible. So we actually need to come back down, pass through, and come back up again on the other side. So this is actually, this L here is equal to lambda quarter. So we end up with lambda is equal to 4L. 1.2 times 4 is 4.8 meter. A small speaker emits sound waves uniformly in all directions. Point P is 20 meters from the speaker. By what multiplicative factor must the power output of the speaker be increased in order to increase the sound intensity level by 20 dB? Okay. Alrighty. So we have that beta is equal to 10 dB common log of I over I naught. Okay. Okay. Okay, let's see here. We need to increase this here. So in this particular case, we actually have a particular I in mind. We have an I. We have an I naught of wherever it is now. And we like this to be equal to 20 dB. Alright, so we have 1/2 is equal to log, right? Nope, not 1/2, that's 2. We can do this yet. 2 log I over I naught. So we end up with 10 squared is equal to I over I naught. Now look at that, there's our answer. Our multiplicative factor. I naught. A train moving due west, that way, at constant speed 24 meters per second. You're moving west. 0. Oh. Train's moving due west that way at constant speed 24 meters per second. You are due west here of the train and traveling east at constant speed of 16 meters per second. Train whistle is emitting a sound frequency with a frequency of 640 hertz. The speed of sound in air is 344 meters per second. What is the frequency of the sound beat? What frequency of the sound beat do you hear? What is the frequency of the sound? Oh, no. What frequency of the sound do you hear? All right, Barbara says, hold on a moment. All right. Where are we at? Doppler shift. VL, L goes on top, FS on the bottom. So we have FL is equal to VL divided by VS, frequency S. Now I need to figure out what these numbers ought to be. All right, so the listener is traveling towards this thing, so we expect it to go higher. The frequency of listener needs to be higher than the frequency source, therefore this is a plus. The train is approaching the listener, therefore we expect it to go higher. In order for this to go higher, we need to make this, in order for this number to be higher, we need the denominator to be smaller, so a minus goes here. Alrighty, so we have 344 goes there, plus the listener's speed is 16 divided by 344 minus 24. Frequency given to be 640. Hertz. There we go. Answer is 344 plus 16 divided by 344 minus 24 and multiply by 640, execute, 720 hertz. Did what I do with the signs make sense? Or any other questions about Doppler shift or anything else I've gone past here in like last 5 minutes? All right. There's a circular hole in a flat brass plate. When the plate has a uniform temperature of 150 centimeters, the diameter of the hole is 2 centimeters. What must the temperature of the plate be to change the diameter of the hole to this much? Coefficient of linear expansion for brass is this much. Alrighty. That's awfully handy of them. Diameter is a linear quantity, so we can do that. Very good. I need to see the equation for that. Where'd you go? Change in L is alpha L naught delta T. Change in L is equal to alpha, which has been provided to us, L naught, change in temperature. What must the temperature of the plate change to for the diameter to increase? Oh boy. Alrighty. Okay. Alright, so it goes, yeah, we're good. So we need the, well, we're going to get the change in T. Delta T is equal to delta L over alpha L naught, and that's it. All right, so it's going to increase by 0.01 centimeters divided by alpha of 2 times 10 to the minus 5. This should be Kelvin. Kelvin inverse. And our initial length is 2 centimeters. Centimeters cancel each other. 1 over inverse Kelvin is Kelvin. So we get change in temperature of a number. Clear that. 0.01 divided by 2e minus 5 times 2. And execute. 250. 250 Kelvin. All right. So that means we need to make this that much hotter. So we will go plus 150. So we have a final temperature of 400 degrees Celsius. Make sense? Did my units do anything funny to you guys? I think we're fine. You mix a certain amount of ice at 0 degrees Celsius with a certain amount of water at 100 degrees Celsius in an insulated container of negligible mass, or infinite infinite specific heat. What is the final temperature after thermal equilibrium has been reached? Assume no heat has been lost to surroundings. We have information about ice, about water, about melting and vaporizing water. Alrighty. That's very handy. Okay. So we have, let's see here. So we need to melt, right? Liquid water at 100 Celsius. Okay. We need to melt the ice. Melt the ice. We need to increase its temperature a certain amount. MC delta T. And that is equal to M water C. This is a delta ice, delta T for the ice, and this is delta T for the water. So then I need to degrees Celsius. I need, and so T delta stuff, right? Does that make sense? Yes, that makes sense. So a delta T is a TF minus T initial. So then, fortunately for us, my T initial here is 0, so we end up with TF. So we end up with MIL plus MIC TF. And that is equal to MWC, and then STF is less than this TF comes up. TF minus T initial. We'll just be careful with that, won't we? So we go ahead and put in a TF minus T initial of 100 Celsius, right? Oh no, I need to be careful here. Much more careful. Much more careful. It's not 0. What is it? 290. 273. Okay. So we end up with, let's see where it goes, TF. TF minus 273.15 is equal to mass of the water, C, and then it's TF minus its T initial, which is 375. Yeah, 370. Oh, careful about it. 373 for decimal 15. There we go. Alrighty. Now we get everything where it's supposed to be. So we have the latent heat of fusion for melting the ice. We have to raise its temperature a certain amount, and that this amount of heat for the ice has to be equal to the amount of heat released by the water. And so now we need to sort through all this algebra here, which is going to be a pain in the behinder. So we have 0.1 and 0.1. Oh, very nice. So the mass of the ice and the mass of the water are the same. That's nice. Mass ice and mass water go away. Divide those away. Very good. L for our fusion is 3.34 times. Let's see, get time in there. Come on. No, I don't want to do that. I would like to have my pencil back. Control Z. There we go. Times 10 to the 5. Alright, no, I'm going to keep doing algebra. I need to keep doing algebra here. And we're writing a whole lot of numbers and then they're going to go all fuzzy on us. Alright. Let's see here. So we have L minus C at T. I'm gonna call this T cold, and I'm gonna call this T hot. T cold plus C T final equals C T final minus C T hot. Get the T final to one side. Oops. Minus. Uh-oh. Something funny to me. When I subtract this CTF to the other side here, it's going to disappear on me, and that's not what I want. And there should be a minus sign somewhere. Oh, I know the problem is. This is a plus here, and this is all equal to 0, so I need a minus sign here. There we go. That means there's a minus sign here and a plus sign here. So now when I move this to, no, no, I was right the first time. I was on the wrong, nope, we're right. I was right. Move this to the other side. So we end up with L minus CT cold minus CT hot is equal to 2C T final. Therefore, T final is equal to L minus C T cold minus C T hot divided by 2C. Now I can write numbers in here. So our L is 3.34 times 10 to the 5 joules per kilogram minus C, let's see here, 4190 joules per kilogram Celsius, or Kelvin. And I'm going to go ahead and add these together. All right, can I do that? Yeah, TC plus T hot. So we end up with, oh boy, a big number. 273.15 plus 373.15. 646.3. Kelvin, all divided by 2, 4190 joules per kilogram Kelvin. Kelvin cancels Kelvin. Joules per kilogram cancel each other. We have an inverse Kelvin on the bottom. Kelvin comes up on top. All right, now we find out if my algebra is worth anything. I feel a little funny about this. Let's see what it is. 10 minus 5. 10 plus 5 minus 4190 times 646.3 and divide. Begin 2 times 4190 and execute. That's not a good number. That's a very, very bad number. Can I do algebra? Oh boy. That's most unfortunate. I can math you up. I got a negative number. That's not good. That was negative 283. Minus 283 Kelvin, which is not a good thing. I should not get a number less than 0. In fact, I should get a number somewhere between 273 and 373. So that means I did some math wrong somewhere, and that's no bueno. Bugger. I'm going to back up and try that one more time, because, yep. I'm going to back that up and try that one more time. Because I have a feeling we're going to see some similar questions again, and so I'm going to make sure that I get this right. Alright, so that was definitely not the answer. Try that again. Idiot checks. I always have an idiot check at hand. So we know we need a number between, our final temperature should be between 0 Celsius and 100 Celsius. And minus 283 Kelvin is not either of those at all. Alright, try that again. Alright, so we are melting some ice. Yeah, what was that? We are melting some ice with latent heat of fusion. And then we are going to warm it up with that mass with a certain specific heat. And it's going to be as delta T. And while we're at it, we are also going to, and that's for ice. And while we're at it, we're going to cool down some water with a certain specific heat, with a certain change in temperature. And no heat is going to leave the system. As it turns out, mass I, Mi, mass of the ice, is equal to mass of the water. Cancel that out. Therefore, LF, and we're all doing this in water. Oops. So don't do anything, just two radical, just yet. CW delta TI plus delta T water equals 0. Equals 0. A change in temperature is equal to TF minus T initial. LF plus CW. So we have two temperature finals minus T initial for the ice minus T initial for the water equal to 0. Solve for TF. Right? So let's see here. I would like this to go to the other side. LF minus CW T ice plus T water equal to CW TF. Divide that back to this side. 2 CW. I think that is what I got the first time. Is it not? What am I doing wrong here? That is not good. Come on. Calorimetry. I know how to do this trick. Why is this not working the way I expected it to? Let's see here. Q, M, yep. MC delta T and ML, yeah. And so this is the heat required to raise the temperature or lower the temperature. Let's see here. 2T F. Let's see here. So T initial for this here is 273.15, and this is 373.15. I got a case of this stupid's coming on, and I don't like it very much at all, because this is the same answer I had the first time, and that's definitely not correct. All right, we're going to cheese it. We need to move on and get this taken care of here. So fill that, not with that color, and then grab the R. And fill it with that color. Come on. Fill it with that color. And grab the R. And then fill it. Nope, that's not what I want. There we go. Fill with that color. Click there. Or there. There we go. Alright, we're just going to basically guess and check this. So then, let's see here. And maybe I'll figure out how to do it the first time. Yeah, well, it's not a mystery, and I should know how to do this trick. Let's see here. Well, we don't need the masses. We just need the L plus the C delta T, which is for the side of 100 is 10.1, and then we should be able to go minus, and then that'll be 100. Minus 10.1, and this should be equal to 0. So punching in the numbers, we guess and check. All right, so L, where's my L? 3.34 E5 plus C of 490 times 10.1 minus 100 plus 10.1. All right, that is not 0. Noticing how that works out, we end up with 2 times 10.1 minus 100. Delete all that. Go on. All right, there's a number. Okay. 39.9. That's a big number. Uh-oh. That's weird. So we have our delta T here, delta T ice. And this is our delta T for the water. So then, minus, that goes there. Yeah. 490. Minus 362. This is rather unhelpful, rather confusing to me. Why is this being so weird? Okay, well, at least now, okay, so let's try this. L plus C, so here's our delta T, minus C at 100 minus delta T equal to 0. So then we end up with L plus 2 delta 2C delta T equals C 100. And then let's see here. Hey, yep, I'm gonna call that weird because I end up with a number doing this cheesy way here. I end up with a number between these two here, which is like, that's not right either. I don't know, Sam Hill, I'm doing wrong here. That's most unfortunate. That's weird. We'll try the next one. We'll come back to it later. A piece of metal with mass of 0.05 kilograms, temperature 200 Celsius is placed into 0.2 kilos of water that is insulated containing individual mass. The initial temperature of the water is 15 Celsius, and after thermal equilibrium is reached, temperature is 20 Celsius. What is the specific heat of the metal in question? Assume no heat is lost to the surroundings. For liquid water, blah, blah, blah. Okay. Okay, so this time we have mass of the water, right? Yep. Times C delta T is equal to the mass of the metal, Cm delta T. Our total is initial temperature and its final temperature. Alrighty. So if anything goes wrong here, at least this should be a minus sign. Alrighty. Okay, so we need to solve for the Cm here. So we have mass of the water, C delta T for it, divided by mass of the metal, delta T for it, metal, water, and that is equal to our Cm. Mass of the water is 0.2 kilos. C is 4190 joules per kilogram Celsius degrees, and as change in temperature goes from 15 Celsius to 20 Celsius, so that's a 5 degrees Celsius increase, divided by mass of the metal, 0.05 kilograms. That cancels there, and it goes from 200 Celsius to 20 Celsius, so that's a decrease of 180 Celsius degrees Celsius. That cancels there, and this number comes out to be 0.2 times 4190 times 5 divided by, begin 0.05 times 180, and execute. There we go. This worked much better. 465.5. Repeating. Units, joules, Kelvin, whatever. kilograms. That's this one here. Yay, we get that. Yay, that worked right. I would have gotten this delta T here would have been negative. So this is actually should actually be a plus equals 0. So then we can do our solving here and actually get the right values in the right places and come up with the correct signs and all that. All right. An insulated aluminum rod has cross-sectional area of this much. So this is going to be a conduction problem and length of half a meter. Thermal conductivity is provided. One end of the rod is maintained at a temperature of 200 Celsius, and the other is in ice water. What mass of ice is melted in 800 seconds by the heat conducted by the rod? All right. So we have that. I need to be writing on the right page. There we go. So we have that the heat transferred is equal to, which is Q on time, is also equal to K A heat temperature hot minus temperature cold divided by the length that the energy needs to travel. I believe that's right. Check that. Yep, good. And Q, for Lippy, Q is equal to ML. Latent heat fusion, MLF. Alrighty. So we have all this information, right? K, we are told is 205. Cross-sectional area of 2 times 10 to the minus 4. T hot is 200. Minus the T cold, which is 0, because it's in ice water. And it will remain that way. And its length is a half meter. So that's 205 times 2e minus 4 times 200 divided by a half is equal to 16.4 watts. Also known as joules per second. And there were 800 seconds multiplied by 800 seconds. And that is 1312 joules. All right. So then this is equal to our ML. So M is equal to 1312 joules divided by 3.34 times 10 to the 5th joules per kilogram. Joules cancel each other. Inverse kilograms comes at the top as a kilogram. Very good. That is a mass. Divided by 13.34 E plus 5. Execute. Not very much. 0.0393 kilograms. All right. A metal sphere radiates energy at 3 watts when the temperature of the sphere is at 27 Celsius. At what rate does the sphere radiate energy if its temperature is increased to 700 and increased to 77 Celsius? All right. Okay. So this is A E sigma T to the 4 T to the 4 is equal to our H here, which we are told is initially 3 watts. I need to cancel out the AE and sigma so that I don't have to bother with them. So I shall. So we do that. So we have AE sigma T initial to the 4 divided by AE sigma T final to the 4. And this is equal to H initial over H final. AE sigma, that is not what it's called for. AE sigma cancels. So then we're told these two numbers and that number there, so now I need to rearrange this. HF, the thing we're looking for, HI is equal to times TF over T initial to the 4th power. All right, yeah, good. So that becomes (3 watts). TF is 77 plus 273.15. 273.15 divided by initial 27 plus 273.15 to the 4th. Clear. 3. Begin 77 plus 273.15 divide begin 27 plus 273.15 end to the 4. Execute. This is 5.56 watts. All right. Adiabatic compression, that's a thermodynamic process that is not on this exam and probably not in this semester. Nope, don't move that. Quantity of gas heated at constant pressure. That's an isobaric process, not on this exam. Monotonic gas increases in volume. Gas does so much work. Temperature is constant, isothermal process, not on this exam. And engine, not on this exam. Carnot heat engine, not on this exam. Quantity of 2 undergoes reversible isothermal process, not on this exam. Undergoes constant pressure expansion, not on this exam. Monatomic gas goes from A to C along the path shown. Was work done for the process, not on this exam. One cycle of refrigerator, not on this exam. Monatomic gas, so you consider monatomic gas, same amount heat and do process A, process B, kept at constant pressure. Volume is constant. Isochoric process, not on this exam. And that's the last question, right? Yep. All right. I'm going to give that one problem another try because it's BS that I can't do it. I should be able to do this problem. And then once we're done with it, I'm going to give one more try. Oh, bother all that. I'll give one more try. This is a thing I should be able to do. As a grad student, this is like a thing I should be able to do. I should be able to handle... Nope, don't do that. I should be able to handle... calorimetry. This is a thing I should be able to do. Unless there are burning questions that I need to answer before I do that. Okay. I'm going to give this one more shot because, God dang it, I should be able to do this. Alright, we are going to melt. I need to melt some ice. I am going to increase its temperature. And I'm going to cool off some water. And no energy is going to go anywhere. Alright. Mass of the ice and mass of the water are the same. I divide that out to the other side. Alright. I have okay, let's see here. I'm going to keep my deltas around. So this is going to be delta I is going to be a T final minus 0 plus C T final minus 100 equals 0. When I combine these, L plus C, I get 2TF minus 100 equals 0. Move the L to the other side and divide by C. 2TF minus 100 equals minus L divided by C. Where's my L? 3.34 E5 divided by C, 4190. Negative 79.7. L is joules per kilogram degrees Celsius. So this is a degrees Celsius, supposedly. Add 100 to that. TF is equal to plus 100, 179, right? Did I do that right? Plus 100. Oh, negative. There we go. 20.3 degrees Celsius. Divide 2 to the other side, and I end up with TF is equal to 10.1 degrees Celsius. There we go. Ta-da! I got an answer. Good gravy. It's modestly embarrassing. All right. Now that I got an answer to that. Any other questions? Any other questions I need to answer, or are we all good? I can answer any question that you would like to pose. Okay. Okay. All right. If there are no further questions for clarification or otherwise, or obfuscation, as the case may be, then I shall go ahead and end my recording and my stream shortly then.